Thanks very much, Venice, and hello and welcome to this month's webinar on rock physics modeling using SynthRock. So this webinar will present three of the most widely used forward modeling workflows, starting with the creation of tuning wedge models, followed by a presentation of the application of Gassman's fluid replacement algorithm, and finally finishing with deterministic modeling of rock properties, taking porosity as an example. Before we proceed further, a quick word about the SynthRock's profile module. The profile module is an easy-to-use tool to quickly run basic forward modeling studies, and it allows the user to simulate a number of geologically realistic what-if scenarios and to investigate their associated changes on elastic and seismic response. So the outline for this webinar is as follows. I'll start with the first workflow of creating simple wedge models, simple thickness wedge models for tuning analysis. Afterwards, I will move on to the second workflow, which describes the fluid replacement modeling using Gassman's equation. And finally, the third workflow will be discussed, which covers rock property prediction, rock property variation modeling using porosity as an example. Also, all the three workflows will be accompanied by an example output result. And at the end, a summary will be presented to conclude this webinar. So the basics overview and the necessary setup required for working with SynthRock has already been discussed in October 2012's webinar, and this webinar essentially is a follow-up to the October webinar. So first things first, how to start SynthRock. Well, you can either go to Analysis, Layer Modeling, SynthRock, and then click on the profile icon. Or alternatively, you can click on this icon in the main toolbar and click on this pop-up window here on the profile icon. So now we are moving to our first workflow, which is creating tuning wedge models. And in this workflow, I will show you how to build simple thickness wedge models from well data, how to generate synthetic seismic data at different bandwidths, and finally how to quantitatively evaluate seismic amplitude variation with layer thickness. So this cartoon illustrates the concepts of creating thickness wedge models in SynthRock's profile module. It requires a well with velocity and density information in terms of logs, and top and base markers corresponding to the interval of interest whose thickness you want to vary. So essentially, the interval of interest is stretched and squeezed to create left and right end of the thickness wedge model by editing the top and base markers of the interval of interest using two control profiles, the left control profile and the right control profile. And in this study, the Oosterhout sand formation found in the F34 well of OpendTect's default F3 demo dataset is used for various modeling exercises for all the three workflows, that is. The Oosterhout sands lie between FS8 marker and a user-picked marker and are approximately 30 meter thick. So the first step of thickness wedge modeling workflow is to add a well with velocity and density logs and top and base markers corresponding to the interval of interest. So before doing that, let's spend a few minutes to discuss the profile module window, which comes up when you click on the profile when you start the SynthRock's profile module. So this is the window, and in here, in the bottom part, you see layer models, and in the top part, you will see synthetic seismic data corresponding to the models that you have created. And further, in here, you have to specify the number of models that you want to create for your modeling exercise. And also, you have to click on this icon to select layer properties that you want to use for your particular work. For example, in this case, I have selected acoustic impedance, density, porosity, P-wave velocity, and water saturation. And I am interested in working with these quantities only. So to add the real well, F34, you have to click here in this area of the main profile window, which says click to add a well. You have to specify the various rock quantity logs, for example, acoustic impedance, density, and P-wave velocity. And you also have to specify the relative position of your well inside the profile mode, which for this demonstration is 70. Now the second step is to add the left control profile and edit the depth of the top and base markers as to have a large thickness of the interval of interest. So to do that, once you have added your well, you click on the left end and select Add Control Profile, which will lead you to this window, wherein you specify the relative position of your left control profile, which is 0 in this case because this is the leftmost end, and you edit the well markers corresponding to the interval of interest such that the thickness between the top marker, that is FS8, and the base marker is 100 meters, for example. Third step is naturally to add a right control profile and make the thickness of the interval of interest 0. So now that you have selected your well and the left control profile, you can right click on the right end and select again Add Control Profile. And the window which pops up after that, you specify the relative position of the right end control profile as 100 and again edit the depths of the markers corresponding to the interval of interest such that the thickness essentially becomes 0. Now SynthRock will generate suitable models in between the two control profiles and the associated synthetic data. And this is how your final model will look like. You have your left control profile, the F34 well, and the right control profile. And in the upper part, you have synthetic data corresponding to the model. Now we are going to look into greater detail at the result of the model, of the thickness wedge model that we have just created. So here you got an acoustic impedance profile which has essentially been generated by zooming in the base, in the bottom part of the main profile window, that is over here, such that you can clearly see your interval of interest between top FSZ marker and the user picked base marker. So you have your thickness of this interval of interest 100 meters on the left, and it decreases to 0 meter on the right. And here you got your real well, which has 30-meter thick Oosterhout sandstone. Now we are interested in creating synthetic data, essentially zero offset synthetic data at different frequency bandwidths to analyze our tuning effects. So to do that, we click on the top left icon of the main profile window that you just seen, which looks like this if zoomed, and select the synthetic type as zero offset stack in the window that pops up after clicking on this icon, and add synthetic data corresponding to various wavelets at different frequencies. So for this example, I have created synthetic zero offset synthetic data using recurve wavelets of central frequency 20 Hz, 30 Hz, 40 Hz, 50 Hz, and additionally a statistical wavelet having a dominant frequency of approximately 60 Hz. And the statistical wavelet is extracted from the seismic data itself. And alternatively, you can also compute pre-stack synthetic data, angle stacks, and AVO gradient corresponding to your thickness wedge models. So here we got our synthetic seismic corresponding to the thickness wedge model, which has been created using a recurve wavelet with a central frequency of 20 Hz. And this recurve wavelet is shown here in the bottom right corner on your screen. Now the same synthetic data profile, but created with the recurve wavelet of central frequency 30 Hz, 40 Hz, and now you can already see that the brightening of seismic amplitude at top FSZ marker, i.e. at the top of the interval of interest, starts to shift towards right. So essentially, with increasing frequencies, your tuning amplitude thickness is decreasing. The tuning thickness is decreasing, to be precise. Now this is the synthetic zero offset synthetic seismic generated using statistical wavelet having a dominant frequency of 60 Hz. Now we can already see qualitatively that, as I said, with increasing frequency of the wavelet, our tuning thickness is decreasing, but we want to do a quantitative analysis. So for that, we can click on this icon on the right hand side toolbar of the main profile window, this icon that is, which will take us to the Crossplot window. And in this Crossplot window, the upper part contains attributes to be computed on the synthetic seismic corresponding to your models, and the lower part houses the attribute set which is applied on the pseudo-water layer properties, which in this example are acoustic impedance, density, PVA velocity, and thickness. So here I have defined a seismic amplitude attribute, and in the bottom part I have defined a thickness attribute corresponding to my interval of interest. And I'm going to extract data for Crossplot along the top FSZ marker, and that is why my extraction window is effectively 0 milliseconds long to make a grid data extraction. If I want to do a volumetric crossplot analysis, I can define a non-zero extraction window here relative to the FS8 marker, for example. And this method can be extended to various attributes available in OpendTect to essentially identify the most suitable attribute for analyzing the tune seismic response. For example, spectral decomposition or instantaneous frequency or anything else that suits your taste. So here is the crossplot between seismic amplitude at top FS8 marker versus layer thickness on the x-axis at various frequencies. So here you can see that the tuning thickness, which is essentially the thickness where your seismic amplitude attains its minima, is decreasing from 62 meters approximately, corresponding to a central frequency of 20 Hz, to 24 meters at a frequency of 60 Hz. So this way you can do your quantitative tuning analysis to approximate the maximum thickness that you can trust in terms of seismic amplitude characterization. So now that we are done with the thickness wedge modeling workflow, we will move on to the fluid replacement modeling workflow, the second workflow. And in here, I will show you how to build simple models of water saturation variation from well data, how to apply fluid replacement algorithm on the models, and finally, how to qualitatively and quantitatively evaluate the effect of fluid substitution on elastic and seismic response. So here is the schematic description of doing fluid replacement modeling in SynthRock's profile module. This model here has a left end with a scaled water saturation log as to have a user-defined average water saturation value in the interval of interest, which could be, for example, 90%. Further, this left end should have the acquired geophysical log data, such as sonic and density. Similarly, the right end has the same water saturation log, but scaled such that the average water saturation now is greater than that of the left end in the interval of interest. Also, the geophysical logs are same as the left end. So basically, the water saturation logs between left and right end are interpolated in between to create pseudo-well models, which are further subjected to Gassman's fluid replacement algorithm, which updates their VP, VS, and density logs and generates synthetic data corresponding to the new fluid fill using the water saturation values of the interpolated models. So the first step of this workflow is to create a pseudo-water saturation log for both left and right ends. So to do that, you again click in the bottom part of your main profile window, which will lead you to this little window, wherein in front of water saturation you can press on create, which will further take you to the rock physics log calculator window, where you can create your scaled water saturation log. Alternatively, you can click on this icon on the main toolbar of OpendTect, which will take you to the Manage Wells window, wherein you click on Create button to move to the rock physics log calculator window. And in here, I would like to point out that you can click on this icon and access a large library of rock physics equations that you can use to create various property types, for example, density, velocity, impedances, elastic ratios, resistivity, and so on, using rock physics equations. And this can be quite handy when you want to create a missing log, for example, from existing logs for a particular well. So now back to our creation of a pseudo-water saturation log. So how do we create the scaled water saturation log such that the average water saturation in the interval of interest is 90%, for example? Well, for this, we analyze the histogram of water saturation log in the interval of interest, i.e. the Oosterhout sense for our case. And using the existing mean of water saturation data in the interval of interest, we calculate an appropriate scalar. Afterwards, we apply that scalar in the rock physics log calculator window on the acquired water saturation log in a well-defined well MD range corresponding to the interval of interest. Outside this MD range, we keep the acquired water saturation log unedited. Similarly, the pseudo-water saturation log corresponding to the right end can be computed. Now the second step of this workflow is to input the two sets of pseudo-well logs at two ends in the SynthRock profile module. So again, back to the main profile window, wherein you click in this area, you specify the well, various geophysical logs, the recently created scaled water saturation log having an average water saturation of 90%, and you put it at a zero relative position, essentially at the leftmost end in the profile module. Once you have added your left control profile, so the left well end, you click on the right hand side and you click on add well again to add your right end well with acquired geophysical logs, which are essentially same as that of the left end, but you change the water saturation log to the scaled water saturation log having an average water saturation of 100% in the interval of interest. And finally, you specify its relative position as 100, i.e. the rightmost end. And once you've done that, your profile window will look like this. So you have defined your model. You have your left end, your right end, and the synthetic seismic data in the upper part. Now, the next step is to define a hydrocarbon column of appropriate thickness in the interval of interest and specify fluid replacement parameters for Gassman's equation. So to do that, the first step is to click on this icon and define a hydrocarbon column. So in here, I have defined a gas column of 30 meters length just below my top FSAT marker, which essentially covers my entire reservoir interval. If you remember, it was of 30-meter thickness. So to apply fluid replacement, the second step is to define fluid replacement parameters, for which you click on this icon on the right-hand side toolbar of your main profile window, which will lead you to this little window, wherein you see the formations which fall under the hydrocarbon column specified by you in the first step. So here content A is the initial pore fluid content and is empty, which means that the wells were modeled with brine as the initial state. Content B is gas and is the final pore fluid content after fluid replacement. And the direction of fluid replacement is obviously from brine to gas. So finally, you need to click on this icon, wherein the forthcoming window you can specify the parameters required for a Gassman's equation. And these parameters basically are bulk moduli and density of the fluid phase and of the rock matrix. Now, after applying fluid replacement, SynthRock will automatically update the VPVS and density quantities and the corresponding synthetic seismic data. Again, it's time to look at the results in a greater detail. So here you've got your water saturation profile, which essentially has been generated by zooming in at the bottom part of the main profile window. So here your average water saturation in the interval of interest is increasing from 90% to 100% in the gas-filled Oosterhout sands. And the acquired water saturation logs in the F34 well having an average water saturation of 95% fall somewhere here at the middle of this model. This is the acoustic impedance profile corresponding to the fluid replacement model that we just created. And you can already see that there is a significant increase in acoustic impedance. When we increase the water saturation from 90% to 100%. Here we have got our zero offset synthetic seismic data after fluid replacement using the statistical wavelet, which is shown here at the right bottom corner. And already visually we can see quite a bit of change in seismic amplitude in the interval of interest. So again, to do our quantitative analysis, we will make use of the Crossplot tool. And we can create crossplots of average acoustic impedance versus average water saturation in the interval of interest, and RMS seismic versus average water saturation in the interval of interest on the right. So from these two plots, we can conclude that the increase in water saturation from 90% to 100% in gas-filled Oosterhout sandstone causes approximately 63% increase in average impedance and almost 75% decrease in RMS seismic. And again, this crossplot analysis can be extended to different seismic derivable attributes, for example, Poisson's ratio, extended elastic impedance, lambda mu rho, to identify the attributes having largest sensitivity to fluid changes, which can subsequently be generated from seismic volume using inversion workflows, for example. And additionally, pre-stack synthetic data and associated crossplots, for example, intercept versus gradient and near stack versus far stack, can be used to evaluate a potential AVO anomaly in the vicinity of the well. Now, the next and the final workflow is to do rock property variation modeling using porosity as an example, wherein I will show you how to build simple models where porosity, or as I said, any other rock property which can impact elastic wave propagation is deterministically varied. I will also show you how to use already as described rock physics log calculator to generate geophysical logs from porosity, and finally I will show you how to qualitatively and quantitatively evaluate the effect of rock porosity variation on elastic and seismic response. So the porosity variation modeling workflow is very much similar to the already described fluid replacement modeling workflow. The model here has a left end with a scaled porosity log such that the average porosity in the interval of interest is a user-defined number, let's say 20%, for example. And the elastic rock properties, i.e. the VP, VS, and density logs, are computed from porosity using rock physics equations. Similarly, the right end of the model has a scaled porosity log, but with an average porosity in the interval of interest which is greater than that of the left end. Again, the right end of model also has VP and density logs calculated from the scaled porosity log. And basically, the models in between the two ends are computed using interpolation of well logs. And just like before, the log data outside this range, outside the interval of interest, is kept unedited as is. So the first step of porosity variation modeling workflow is to create a pseudo-porosity log for left and right ends. So this is again similar to creation of a scaled water saturation log, which has already been described. So again, you analyze your histogram of the porosity data in the interval of interest, and you compute an appropriate scalar which, when applied in a well-defined MD range corresponding to your interval of interest, will scale down your acquired porosity log such that the average porosity in the interval of interest between this MD range, that is, will become 20%, for example. And again, outside this MD range, we will keep the acquired porosity log unedited. Similarly, we can compute the pseudo-porosity log corresponding to the right end of the model. So now the second step is to create geophysical logs, for example, velocity and density from porosity at both ends using rock physics equations. So for this demonstration, I am using well data crossplots in the interval of interest to establish velocity porosity and density porosity linear relations. Alternatively, and preferably, more advanced well data calibrated rock physics equations can be used. For example, Ramus porosity to velocity transformation equation. So again, using our rock physics log calculator window, we can define within a specific MD range a pseudo velocity log using the linear equation that we have just derived from the well data crossflows. And outside this MD range, we will keep the acquired velocity log unedited. And we will also do it for the right end to compute the pseudo velocity log from the scaled porosity log having an average porosity of 40% in the interval of interest. Same workflow is used to compute density log for both the left and the right end. Now that we have created our two sets of pseudo logs, it's time to input them at two ends in the SynthRock profile module. So to achieve that, we again click on the bottom part of the main profile window here, click to add a well. We start with specifying the relative position, which is 0 here, as we are defining our left end at the moment. We select the well, and here we select the various geophysical logs that we have just computed from a scaled porosity log having an average porosity of 20% in the interval of interest. Once we have done that, we can right-click at the right end to add well. Now we specify its relative position 100, i.e. the rightmost end. We use the same well again, but with various geophysical logs which have been created from a scaled porosity log having an average porosity of 40% in the interval of interest. Once you've done that, you will see your final porosity model, which will look like this, wherein you have your left end, your right end, and the corresponding synthetic seismic data in the upper part of the main profile window. Finally, SynthRock will interpolate the well logs between two ends to create pseudo-well models and associated synthetic data. Again, it's time to look at the results in more detail. So here we have got our porosity profile, wherein the average porosity in the interval of interest between top FS8 and user-picked base marker is increasing from 20% to 40% from left to right. And the acquired porosity log in F34 well having an average porosity of 35% lies at this position. Here you've got your acoustic impedance profile corresponding to the porosity variation, and again it clearly shows a big enough change in acoustic impedance as you increase your average porosity in the interval of interest from 20% to 40%. Just like before, we have created a zero offset synthetic seismic corresponding to the porosity variation model, and we can already visually see an immense change in the seismic character corresponding to an increase in average porosity in the interval of interest from 20% to 40%. And the final step again is to do a quantitative analysis using the Crossplot facility. So here we have generated our average acoustic impedance versus average porosity crossplot in the interval of interest in the Oosterhout sense on the left, and RMS seismic versus average porosity crossplot on the right. And as described previously, you can crossplot different seismic durable attributes for example, acoustic impedance, elastic impedance, lambda mu rho, to identify the attributes having largest sensitivity to porosity changes. And this workflow can, this entire workflow can be modified to model the variation of any other rock property having impact on elastic and consequently the seismic response, which could be volume of shale, volume of clay, total organic content, etc., instead of porosity. Now, finally, I will conclude this webinar by presenting a summary. So, first of all, OpendTect SynthRock profile module allows a quick investigation of what-if scenarios from well data to predict rock property variation effects on seismic data in a geologically sound way. Both qualitative and quantitative type of analysis can be performed for tuning wedge models, fluid replacement modeling, and deterministic rock property variation. And finally, the forward modeling workflows presented during this webinar can help in a quick evaluation of seismic derivable attributes which are best suited for a particular geophysical or geological objective, such as dew tuning of the seismic response and rock property predictions, and additionally AVO signature of potential fluid or lithology anomalies in the vicinity of a well can be evaluated. So with this, I conclude this month's webinar on rock physics modeling using SynthRock. And thanks very much for your attention. So back to you, Venice, for the Q&A session.
Okay, thank you so much, Hardeep. Actually, we have a very active session because I kept receiving some questions. Arno, are you there?
Yes, I do.
Okay, good. I send you a couple of questions if you would like to read them and explain the answer.
Yes, there's one question where that I read out it. Ask if we really interpolate VP and density by making a linear relation with a porosity. That is the case that has been presented here. However, in the rock physics toolbox, you are free to use any relation between porosity, VP, and density that you can take. So a linear relation is the most obvious way to start, but it's really up to the interpreter to decide how to relate the rock properties together, and what equations, what model to use to relate these various rock properties.
Okay. We have another question from. The question says, "Do I understand right that you just enter?" Do you see that question from Ila Tishinoku?
Yes.
Okay.
Yes. I hope I answered it.
Yeah, because he has a follow-up question. Could we have a look at
Yes, the other question is, doing rock physics modeling, we assume that we should have a direct relation between the modeled property, V shale, and VP rho B. It's not the case. The assumption is really the one you input when doing the rock physics analysis and when creating your varying VP and density from varying porosities. So as I said, you can input a linear relation, or you're free to use a more complex law to relate your rock properties together. Especially, and that has not been presented, but that is a bit outside of this webinar, in the stochastic module, you can relate more effectively your rock properties using probability density functions. But in general, in a simple wedge model, you don't use very often all the complexity of the logs.
Okay, thank you. I have another question I assigned to Hardeep. Hardeep, did you see it?
Not yet.
It's
Venice.
from Van Dyke. I just sent it to you. It says, to what extent we can do rock physics without recurse to log, i.e. do rock physics. Did you see that from totally geophysical surface measurements?
Yeah, I can see this question right now.
Okay, would you please answer it for us?
Yeah, sure. Yeah, you can manually specify, at least for a fluid replacement algorithm, the porosities, water saturation value, or Poisson's ratio that you expect in your subsurface. But except from that, you cannot do much if you do not have access to the petrophysical properties, i.e. the porosity, water saturation, volume of shale, volume of clay, because you cannot relate them with elastic or seismic response if you don't have them. But for, as I said, with Gassman fluid replacement algorithm, you can still do a bit of work. If you do not have access to porosity, water saturation information, you can still enter a constant number and apply your fluid replacement algorithm.
Okay, thank you. There is another question from Omar Muhammad. I gave it to Arno. How can I calculate the relative position of the well when I add the well to the seismic profile? Arno, can you answer for us that question?
Yes, Venice. This is something you can best compute from the 3D OpendTect scene by using the measure distance tool. With the measure distance tool, you can compute the distances between your wells, and that will allow you, well, you still need to do some math to translate them into relative positions, but that's how you do it.
Okay, good. Okay, we have another question also. Somebody's asking, is SynthRock available now?
SynthRock is, what you have seen is the latest stage of development. So as you can see, it's very quick, very close to the end of the development stage. However, we are still we still want to do some final refinements on the product, and as a result, it's we expect to release it with the release candidate of OpenTect 4.6 before the summer, but it's very likely that the final public release will be for after this summer.
Okay, thank you. I assigned another question from Steve Adak to Hardeep. Please discuss the analysis of, did you see that?
Not really. Not yet.
Okay. It says, please discuss the analysis of wavelet effect of the wedge model.
Yeah, now I can see this one. Yeah.
Okay.
Yeah, well, wavelet effects on the wedge model will always be there. I mean, as such, because this is the way it is. So, in the description that I made, my objective was to have various wavelets with different frequencies to analyze the seismic amplitude variation corresponding to the thickness changes in the interval of interest, and to do a more sophisticated analysis of wavelet effects, we can design a constant thickness model and see how the seismic data changes with changes in the wavelet. I hope this answer to some extent, at least, satisfies the asker.
Okay. Thank you, Hardeep.
Yes, I would like to add that.
Yeah.
I would like to add on this thread that the wavelet is really added at the very end of the workflow because first the wells will be interpolated and the wavelet will have absolutely no influence of how the well log properties will be interpolated. A wavelet will be only used at the very end when convolving the reflectivity logs from the pseudo-wells to the wavelet in order to get the synthetic seismic trace. It really comes at the very, very end of the workflow.
Okay, thank you. Arno, I assigned you another question from SynthRock again. I'm looking for a way of viewing changes. Did you see that question?
Yes.
Okay. Can you read it for everyone, please?
Yes. The question is, I'm looking for a way of viewing changes in wavelet choices and central frequencies that is somewhat interactive, not just creating lots of plots and values you need to compare. In OpendTect, you'll have the possibility to generate, and these are some of the wavelets you have seen during this webinar, synthetic record wavelets with a given central frequency. So it's rather easy to have, within a minute, 5, 6, 7 different wavelets with each another central frequency. And you have to keep in mind that in SynthRock, most of the work is done on the fly. So at no time you'll create any volume on disk. The synthetic data sets are created on the fly. So you're able to specify your 5, 6 different synthetic data sets that are all based on the same reflectivity logs from the pseudo-wells, and you assign to each another wavelet. And doing so, you can very quickly toggle in the interface. Perhaps you can show us this, Hardeep, on one of your slides, where you can toggle between the synthetic data sets, and that will allow you to toggle in SynthRock, just like Hardeep did during this webinar on the slides. There's a very quick combo box, how we call it, at the top of the SynthRock window, where you can toggle between the various data sets.
Oh, sorry, it's this one. Let's see. Yeah, so it's here where you can change the currently displayed synthetic seismic data.
Yeah, so it's a list showing all the defined synthetic seismic data that are either zero offsets, but you could also define pre-stack data store or under stacks. And so it's a roll down list, so you can very quickly browse through the various quantities. In the same way, you can browse, and that's where I go back to another question that just came in. You can browse into the various rock properties from the pseudo-wells, and this you can do in 2 ways. At the base of the SynthRock window, you see the rock properties in depth. So you see the pseudo-wells one next to each other. And there is a similar combo box that allows you to browse through the various quantities in depth, displayed in continuous cross variable density. Also, at the same time, you can display your rock properties from the pseudo-wells converted from depth to time by using this menu variable density view that would allow you to see the interpolated rock properties behind the wiggles, because in this view you see first a wiggle display and a variable density display, which can be one of the rock properties of your layer model, of your simulation.
Okay, thank you. We have another question. Say, could you please answer regarding the weaving intermediate logs?
Yes, well, that was my answer to it.
Okay, so you answered Steve and that as well. Okay.
Yes.
Right, any more questions? That was very active session. If anybody has any more questions. Okay, that's very good. We thank you all for attending our webinar today. And thank you, Hardeep, and thank you, Arno, for answering the questions and the presentation.
Thanks, Vanis. Thanks, everyone.
Thank you.
Actually, I just would like to tell you, if you are the first time with us, that this webinar is recorded and it will be sent to you within a few days. And also, it will be posted in our Facebook page and LinkedIn page. If you have any question, and if you after you listen to it again, please feel free to just email us. Our address is webinar@dgbes.com. And at the end, I would like to thank everyone again, and just to let you know that we will have a summer vacation, that you can enjoy your summer for July and August. And then we will come back again on September to start our monthly webinar, and we will send you the invitation for that. Okay, thanks everyone, and see you in September.